If a model has several uncertain inputs and you enter an at-risk function such as risk normal in each of their cells, the uncertain inputs are treated as if they are probabilistically independent. However, quantities in the real world are often correlated to some extent, either positively or negatively. If you know that the uncertain inputs are correlated, and you can measure the extent of their correlation, you should account for this correlation in your model by using at-risk's RiskProject function. It is usually difficult to gauge how much this actually matters. This depends entirely on the specific model, but there is no excuse for assuming independence when you know it isn't realistic. This video illustrates how to do it. The model shown here assumes that you are going to invest certain percentages of your wealth for some period of time in two stocks and a commodity such as gold. The returns are assumed to be normally distributed with given means and standard deviations. And they are fairly highly correlated. The two stocks tend to change in the same direction, which tends to be the opposite direction from the commodity. For now, focus on columns H to J. The quickest way to build this correlation behavior into the model is to first enter the usual risk normal functions, or whatever distributions you want to use, in the uncertain cells in row 14. Then select these cells, the middle group of green cells in columns H to J, and click the Define Correlations button on the at-risk ribbon. This opens the following dialog box, where you can define a correlation matrix. You give the matrix a name, such as Core Matrix 1. You specify the location for it on the spreadsheet. And you specify the correlations. Actually, only those below the diagonal are required, by typing numbers in the boxes. So stocks 1 and 2 are highly positively correlated, and gold is negatively correlated with the two stocks. By the way, if the dialog box doesn't look like this when you open it, you probably forgot to select the input cells first, which is a common mistake. In this case, you can cancel out, select the input cells, and try again. When you click OK, the model changes automatically. It now includes the correlation matrix in columns H to J, and the formulas in columns H to J of row 14 now include the RiskProject functions. For example, the original formula in I14 was the same as in cell D14, just the risk normal. Now it includes a third argument, the RiskProject function. The last two, right here, indicates that this is the second of the three correlated variables. The formulas in H14 and J14 are similar, but they have indexes 1 and 3, meaning that they are the first and third correlated variables. 1 and 3. If you prefer, you can skip the Define Correlations dialog box and type the formulas directly, but this will probably take a little more time and increase the chance of making a mistake. If you do it this way, you should first enter the correlations you want directly into cells, optionally range name the correlation matrix something like Core Matrix 1, and then enter the entire formulas, including RiskProject, in the uncertain cells. Note that there are 3 sets of asset returns in the model, just for comparison. Those on the left are for the case of independent returns, so there is no correlation matrix. Those on the right are for the case where the minus signs have been omitted from the correlations. Now all returns will be positively correlated. I will generate its correlation matrix and its RiskProject functions in the same way as before. plus 0.6, and plus 0.7. Before continuing, it helps to know, at least conceptually, what at-risk does when it runs a simulation with correlated inputs. When it runs, say, 5,000 iterations of a simulation, it first generates 5,000 random values for each of the correlated variables from the specified distributions, in this case, the normal distributions. Then it shuffles or rearranges these sets of 5,000 numbers so that they have the desired correlations. For example, the 5,000 stock 1 and 5,000 stock 2 returns are shuffled in such a way that low values tend to be paired with low values and high values tend to be paired with high values. Now I will run the simulation for 5,000 iterations. Here are the histograms of the portfolio returns. There is independence, there is negative and positive correlations, and there are all positive correlations. The corresponding summary statistics found with at-risk's statistical functions are shown below. They allow you to compare the three cases. First, note that the three mean returns are almost identical. This is no coincidence. Averages aren't affected by the shuffling just described. However, the correlations do affect the variability of the returns. As you can see from the standard deviations and the 5th and 95th percentiles, the portfolio return distribution with positive and negative correlations is less spread out than the distribution with independent returns. And the opposite is true for the model with all positive correlations. It's more spread out. This might not have been immediately apparent from the histograms, but they have different scales on the horizontal axis, which makes them harder to compare. The all positive correlations model is the case of putting all your eggs in one basket, whereas the positive negative correlation model applies to the investor who diversifies. The diversifier has a safer portfolio, whereas the all eggs in one basket investor has more upside potential, but also more downside risk. For each of these models, you can check the actual correlations of the simulated data. To do so, select any cell in a correlation matrix and click the Browse Results button. You see a matrix of scatter plots of the correlated values, along with their sample correlations. Of course, the sample correlations should be close to the correlations you specified. Any differences are the results of sampling error, and these differences will decrease with more iterations. Before concluding this video, I will point out one other feature of at-risk's defined correlations tool. There are some sets of correlations that aren't valid, even though all of their values are between -1 and +1. They are invalid in the sense that no data set could ever have these correlations. I will illustrate one possibility, using the correlations -1, 0.9, and 0.9. When I click this button right here, it checks for matrix consistency. If I say check matrix consistency, I get this dialog telling me that it is not consistent. If I click yes, at-risk will do its best to find values reasonably close to the ones I entered, and in this case it will use the values shown. Actually, at-risk has an option that gives you more control on how the correlations are adjusted, but I won't cover them here. Summarizing, the point of this example is that when it makes realistic sense that uncertain inputs are correlated, either positively or negatively, It is important to build this behavior into the model explicitly with at-risk's RISKOrmat function. If you don't, and instead assume independence, the results can be quite misleading. There are some general principles for choosing appropriate probability distributions for uncertain inputs in an at-risk simulation. For example, you can sometimes narrow the choice by assessments such as 1. The quantity must be between 0 and 100. 2. The quantity can have only a few discrete values. Or 3. The distribution of the quantity is skewed to the right. Another approach is to fit possible distributions to historical data on the quantity of interest. Of course, historical data are not always available, but when they are, at-risk distribution fitting tools can be used. These tools automatically rank candidate distributions on their goodness of fit to the data, and then you can make the ultimate choice of the distributions you want to use. As an example, the data set you see here contains 3 years of weekly demands, 156 observations, for a company's product. If a simulation model requires demands in 1 or more future weeks, it is natural to use a probability distribution that fits the historical data well. To find good fits, click the Distribution Fitting drop-down on the At-Risk ribbon and select Fit. Actually, if you already have fit a distribution to the data, it is shown at the bottom of the Distribution Fitting drop-down list, and you can choose it directly. Now, given this resulting dialog box, select the data range and the type of data. The data range should not include the top row that has the variable name. And I'll make this continuous data as opposed to the other possibilities. Next, click the Distributions to Fit tab and select the candidate distributions you want to try. Specifically, once you make some choices about the data in the left side, such as a lower bound of 0, and you're not sure about the upper bound, At-Risk checks all the continuous distributions that satisfy these conditions. If you have never heard of some of these distributions, you can uncheck them, as I will do here. Then you can click Fit. At-Risk fits each of the checked distributions to the data. It ranks them on goodness of fit, and it shows you the results graphically and numerically, as you see here. For these data, the best fits are the gamma, the Weibull, and the log normal, 3 very popular right-skewed distributions of positive quantities. You can see these fits in the graph, where the red curve is the gamma distribution, the green curve is the Weibull, and the purple curve is the log normal. The blue bars represent the histogram of the data. Actually, you can check any of these distributions on the left to see how well they fit the data in the graph. For these data, the triangular and exponential fits are not nearly as good. At-Risk actually ranks the distributions on 5 criteria, the first 2 of which, AIC and BIC, are new to At-Risk 6.0 and are preferred. The other 3 are chi-squared, Anderson-Darling, and Kolmogorov-Smirnov. The rankings can be slightly different depending on the criterion used. For this data set, the gamma, Weibull, and log normal distributions are the top 3 on all of the criteria. At this point, you could enter any of the formulas you see up here into a cell in the worksheet as the demand for some future week. Even easier, you can click the Write to Cell button to enter either of these distributions in a cell of your choice. I will do it for the gamma. Because of the good fits, you can feel comfortable that you have chosen a reasonable probability distribution for demand. Actually, you get some new options, as you see here, in At-Risk 6.0 when you click the Write to Cell button. Specifically, if you select Linked updates each new simulation option, At-risk checks whether the data have changed when you run a simulation. If so, it refits the specific distribution with the new data. For example, if you choose the gamma distribution, it will find updated parameters of the gamma distribution when you start a simulation. In contrast, if you select the Live Updates Whenever Data Changes option, At-risk immediately refits and returns the best distribution whenever the data change. It accomplishes this with the new RiskFitDistribution function shown here in the dialog box. I'll try this one. Here is the RiskFitDistribution, and the corresponding cell comment reminds you of the gamma parameters. For example, the alpha parameter is 2.5657. If I now change some data, the parameters will change. As you can see, it's 2.7049 for alpha now. Also, with this cell selected, you can review the fit from the distribution fitting dropdown. There it is. Another change in At-risk 6.0 is the addition of the bootstrap option. If you choose this option when fitting a distribution to data, At-risk samples from the distributions being fitted to find distributions of their parameters, including confidence intervals for these parameters. I'll try it. By the way, notice there is the demand data that we already used. I'll just choose it. It remembers the settings. Then Bootstrap, I will run Bootstrap, 1,000 resamples with 95% confidence level. This takes a little bit of time. If you check this option, the next to last button below the fit graph is enabled. If you click it and select parameter confidence intervals, you get a graph like this one. This gives you 95% confidence that the alpha parameter for the gamma fit is between 2.203 and 3.427. There is one other important addition in At-risk 6.0, the batch fit option. This can be used when you have multiple adjacent columns of related data, as you see here. In this case, batch fit allows you to fit distributions to all of the columns simultaneously. This not only saves time, in contrast to fitting them one at a time, but it also provides the option of estimating correlations between the data variables. The user interface for the batch fit is very similar to the interface for the fit tool, except that there is now a report tab. Again, I will not include the variable labels at the top. I can pick the distributions to fit, just like before. And in the Report tab, I can include correlations. I can place the report in a new workbook, or if I uncheck it, it will be in this workbook. And I can include a detailed report worksheet for each fit. The batch fit results include a fit summary worksheet with the best fitting distribution to each of the data variables: triang, log normal, Weibull, exponential, along with a matrix of estimated correlations. And further information about the fits for each variable appears in separate worksheets. Note that there are formulas in row 9 of the fit summary worksheet, like this one, including the RiskCormat because of the correlations. You could copy these as part of a simulation model that requires values for these 4 variables. When you run an at-risk simulation, at-risk allows you to filter either inputs or outputs in several ways. Probably the most frequently used filter is to filter out extreme values in one or both tails of a distribution, but this is only one of many possibilities. You can create filters from the Define Filters button on the At-Risk ribbon, or you can do it with the Filter button on several at-risk report windows. I will illustrate the possibilities on the model of discounted cash flows shown here. This model was adapted from one of the at-risk example files. The uncertain inputs appear in green font, and the single at-risk output, NPV, appears in maroon font. The Define Filters button lets you restrict input or output values by conditions you impose. As you can see, this button is disabled until you run a simulation. So the first step is to run the simulation. The distribution of NPV without any filters is shown here. It will be useful to keep this graph in mind as filters are added. For example, around 250,000 for the 95th percentile. Then you will see the effects of the filters. The Define Filters button provides several options, two of which are illustrated here. First, you can apply a filter to an input. I will do it here. There are three options. It's either off, standard, or iteration. I will use iteration. I will make the percentiles the 25th and the 75th. And I will apply this filter. This filter restricts the annual revenue growth rate to be between its 25th and 75th percentiles. Remember that the simulation has already been run, so some of the iterations had growth rates beyond these limits. However, when you click Apply and then browse the NPV result, you will see results only from the iterations that satisfy the filter conditions. In other words, you will see the output distribution only for the restricted range of this input. However, to get this behavior, you have to select iteration as the type. Here is the filter distribution of NPV. It turns out that the annual revenue growth rate has a large effect on NPV. So by restricting the values of this input to a narrower range, the NPV is also restricted to a much narrower range. For example, the 95th percentile was originally about 250,000. Now it is only slightly above 100,000. If you change the type of filter for this input from iteration to standard, the effect is less interesting. Now only the graph of the input is affected, as you see here. The graph of the NPV output reverts back to its original form. The second use of the Define Filters button is to apply a filter to an output. This can be used in conjunction with or instead of a filter on an input. Here I will use the latter option. So the first step is to clear the filter on the input. Now I will create a filter on the output, NPV. Its type can be either standard or iteration. They both have the same effect. And I will restrict it to be between the 10th and the 90th percentile. Now I will browse NPV. And I see only a restricted range of values, the middle 80% of the NPVs. An alternative way to apply the same types of filters is through the Filter button at the bottom of several at-risk results windows. For example, to apply a filter to an input, you can select the input cell, click Browse Results, click the Filter button, and you get the same options as before. You can also apply a filter to an output cell in exactly the same way. To clear any or all filters, you can click the Define Filter button, highlight the filters you want to clear, click the Clear Filters button, and click the Apply button. Now there are no filters. You might be familiar with the goal-seek tool in Excel. It is used for solving one equation in one unknown. Specifically, it allows you to force a formula cell to equal a desired value by varying the value in a selected cell. For example, in a break-even model, you might want to find the sales volume required to break even, that is, to force profit to zero. At Risk has a very similar goal-seek tool found under the Advanced Analyses dropdown. The difference is that it allows you to force a summary measure, such as a mean, standard deviation, or percentile, of an output cell to a desired value by varying the value in a selected cell. As an example, suppose you want to find the transaction capacity in this e-commerce model that forces the mean profit to 230,000. The mean is currently about 200,000 when the capacity is set to 2 million. You can see this when I run the simulation. There's 200,000 approximately. To force mean profit to 230,000, I will select Goal-Seek from the Advanced Analyses dropdown and fill in the resulting dialog box as shown here. Want to force profit, actually the mean of profit, to 230,000 by changing the capacity cell. You can speed up the search by adding lower and upper bounds on capacities to search in the Options dialog box. I'll make it 1 million and 2 million. The tighter the bounds, the quicker the search. Also, note in this dialog box that only an approximate answer is guaranteed. The mean profit will be within 1% of the desired value. The reason is that it might take too long to find a more exact value. Now I will click on Analyze. And it does a search, and the result you can see here. Your results might differ slightly because of the random numbers generated. It says to use a capacity of 1.2 million approximately. Of course, this doesn't imply that a capacity of 1.206 million will lead to a profit of $230,000. It only implies that this capacity will lead to a mean profit of approximately $230,000. Actually, if you run at risk again with this capacity, you will not get a mean return of exactly 230,000, but it will be reasonably close. I'll try it. Close to 230,000. In fact, if you run Goal-Seek again, it is very possible that it will report a slightly different capacity, again because of randomness. Slightly different. As stated earlier, you can force any summary measure of profit to a desired value with Goal-Seek. For example, with a capacity of 2 million, the standard deviation of profit is a little over 290,000. I'll show that. I will use Goal-Seek to reduce this to about 200,000. Standard deviation of profit to 200,000. As you can see, the required capacity is about 1.73 million. Using that capacity, let's see what the standard deviation is. About 200,000. This video illustrates one of at-risk's advanced tools called stress analysis. This tool is usually used to find the distribution of an uncertain quantity, given that it is either relatively small or relatively large. In technical terms, it is typically used to find the conditional distribution of an uncertain quantity, given that it is in one of the tails. Here's a typical example where stress analysis is useful. Suppose that you own an asset, such as a home, that is at risk to certain damages, such as damages from an approaching hurricane. You believe the potential uncertain damage amount is log normally distributed, with mean 200,000 and standard deviation 100,000. This implies a fairly long tail to the right, where the damage could be huge. Your actual loss is based on the damage amount. It could be the damage amount itself, but in this model, your loss is assumed to be the damage amount if the damage amount is less than 300,000, and otherwise it is the damage amount raised to the 1.1 power. This means that your loss is magnified for large damage amounts. Now, suppose you decide to purchase an insurance policy that will shield you from really large losses. Specifically, the policy stipulates that you will incur the entire loss if the damage amount is less than or equal to the 90th percentile of the damage distribution, and the insurance company will incur the entire loss otherwise. There are several questions you might ask about such an arrangement. First, what is the distribution of loss the insurance company faces? Second, what is the distribution of loss you face? And third, what amount is the insurance company likely to charge you for this policy? At-risk's stress analysis tool can be used to answer each of these questions. I will answer the first question, how much the insurance company stands to lose, by finding the conditional distribution of the loss, given that the damage amount is greater than the 90th percentile of the damage distribution. To do this, I will set up a stress analysis from the Advanced Analyses list. I will monitor the loss in cell C6, and I will add an analysis. The reference cell is the damage cell, C3, and I want to stress high values, those above the 90th percentile. The Stress Options dialog box contains various settings. I will ask for the checked charts and place results in a new workbook. Now I will click Analyze to find the conditional distribution of the large losses the insurance company faces. The results actually show a comparison between the baseline distribution of the loss with no insurance policy and the conditional distribution of the loss faced by the insurance company. You can see this numerically in the summary sheet or in the two chart sheets. For example, the mean loss in the baseline case is about 340,000. But the conditional mean loss the insurance company faces is much greater than this, about 1.53 million. However, keep in mind that this is conditional upon the event that the damage is greater than its 90th percentile, and this occurs only 10% of the time. In other words, if the insurance company has to pay, its mean loss will be about 1.53 million. But there is a 90% chance it won't have to pay. Therefore, its mean loss overall is only 10% of 1.53 million, or 153,000. This helps to answer the third question. Specifically, the insurance company will charge at least 153,000 for the policy, and it will undoubtedly add a bit more to make a profit. Finally, to see the loss you face with such a policy, aside from the price of the policy itself, I will run another stress analysis, this time stressing low values up to the 90th percentile. Now the results compare the same baseline as before to the conditional loss you face. For example, your conditional mean loss is now about 208,000. Again, however, remember that your chance of incurring this loss is only 90%. The other 10% of the time, you incur no loss because the insurance company protects you. Therefore, your actual mean loss is only 90% of 208,000, or about 187,000. Of course, you have to add the cost of the insurance policy, at least 153,000, to this. And depending on what the insurance company actually charges you, your total mean loss could be larger than the mean loss with no insurance. That is the $340,000 from the baseline case. However, you now face less risk in the sense of really large losses, so you might welcome a slightly larger mean loss to avoid the risk. At-Risk has a very powerful tool, its Simulation Scenarios tool, for discovering which uncertain inputs are most responsible for driving outputs to specified ranges of values, usually abnormally large or small values. The concept is fairly simple, but the way At-Risk implements this is more complex. This video will walk you through the procedure. Here is a model of sales of a new product. It is adapted from one of the At-Risk example files. There are several uncertain inputs in the cells with green font, and they lead to the single at-risk output, the NPV of profit, in the maroon font. A typical scenario analysis is the following. In a simulation of, say, 5,000 iterations, the NPV output will be above its 75th percentile in a quarter of the iterations, that is 1,250 iterations. In these 1,250 iterations, which of the inputs are most different from their values in all iterations? For example, when NPV is this large, does the initial unit cost tend to be abnormally small? Does the early annual demand growth tend to be abnormally large? Do any of the inputs in these 1,250 iterations tend to have about the same values as they have in all iterations? You can answer such questions by running the simulation, browsing the NPV output, and clicking the % button in the Browse Results window. This brings up the following choices. I will select the first. You then see this tornado graph. By the way, the results are highly dependent on the random numbers you happen to generate. You might see a slightly different tornado graph. In any case, the short story is that only two of the inputs, the product lifetime and the initial demand, are, quote, significantly different in the iterations where NPV is above its 75th percentile than in all of the iterations. In this case, they are both larger. The other inputs are not significantly different. The longer story involves at-risk's meaning of, quote, significant, and the numbers in the bars. For each input, this is based on three numbers: the median and standard deviation of the input in all iterations, labeled here as M1 and S1, and the median of the input in the iterations where the output is above its 75th percentile, labeled M2. If the absolute difference between M1 and M2 is greater than half of the standard deviation, the difference between medians is considered significant, and it gets a bar in the tornado graph. The percentage shown in the bar is the percentile where M2 falls in the distribution of the input for all iterations. For example, M2 for initial demand is at about the 70th percentile of the initial demand distribution. This is much higher than where M1 falls, which is at the 50th percentile by definition. The other number in the bar is M2 minus M1 divided by the standard deviation. That is, it is the number of standard deviations that M2 is above or below M1. For example, the product lifetime's median for large values of NPV is 1.11 standard deviations above its median for all values of NPV. Now you know the technical details, which you can revisit as necessary. The rest of this video focuses on the at-risk interface. First, you can drag any of the bars in the tornado graph off the window to get the following type of scatter plot. The blue points are where NPV is above its 75th percentile, and the red points are all iterations. This clearly shows that the product lifetime input tends to be larger when NPV is large. The blue points tend to be toward the right. Second, from the tornado graph window, you can click the % button and select Edit Output Scenarios to get the following dialog box. The three scenarios you see are the defaults, but you can change them in many ways. For example, you can select actual values, and then for the first scenario, change this to less than $250,000. This is about the 8th percentile of the NPV distribution. Then the tornado graph changes as you see. In this case, 4 inputs are significant. The top 2 have lower medians for this scenario, and the bottom 2 have higher medians. In this case, the values shown in parentheses in the bars are the actual values. That is, the medians of the various inputs when NPV is larger than its 75th percentile. Third, you can click the % button below the Define Filters button on the at-risk ribbon. This opens a highly interactive window with all the same options for specifying scenarios. It has 2 drop-downs at the top and a row of buttons at the bottom, and they are all quite straightforward. For example, if you click the middle button at the bottom, you see a matrix of scatter plots. Then you can drag any one of these off the window to see an expanded version of it. Finally, you can select scenarios from the Excel Reports button and you see essentially the same report as the one I just showed, but now it is in a separate worksheet window. This version isn't interactive. In summary, when you perform a scenario analysis in at-risk, keep the big picture in mind. Although the details are somewhat complex, the goal is quite simple. You are trying to see which inputs are primarily responsible for an output being abnormally large or small. At-risk has a number of built-in functions called property functions. You can see a list of these in the Insert Function drop-down list. All of these. There is no common theme to these various functions, so it is somewhat difficult to describe them as a group. You will typically see them when you add input distributions or when you add at-risk outputs. They are essentially tacked on to the input distribution functions or the risk output function, and they are typically used to describe the inputs or outputs in some way. As a simple example, suppose you select an output cell and click the Add Output button. This suggests a name for the output, but you can override it to say revenue. Then you will see that the function risk output of revenue has been added to the formula. However, there is another way you can do this. From the Add Output dialog box, if you click the FX button, you see this dialog. If you fill it in as shown, revenue, dollars, and I'll specify continuous, you see how risk output has been changed. The first three arguments of risk output are reserved for the name, the range name, and the position in the range, respectively. These latter two arguments aren't used here, hence the extra 2 commas. But the final two arguments you see are the property functions, risk units, and risk is discrete. In this case, their values will be reflected in at-risk output graphs and reports. Another use of property functions for an at-risk output is in a Six Sigma quality control setting. Suppose the output must be between lower and upper specification limits, LSL and USL, of 172 and 228, and it should have a target of 202. Then when you add the output, and click the FX button, you can give it a name and units, and you can click the Six Sigma tab and fill out the resulting dialog box as shown. Click OK. Click OK. And you can see that now there is another property function, the risk Six Sigma function, with the arguments that I specified. There is also the units, risk units property function. Now I will run a simulation for that output. As you can see, the histogram of the output shows the specification limits, the target, the name, and the units. Property functions can also be added to input distribution functions, again to describe or modify them in some way. The easiest way to do this is by clicking the FX button to the right of the cell formula box in the Define Distributions window. There's the normal distribution. I will click the FX button to open this dialog box. I'll fill it out as shown. With these settings, the distribution formula changes as you see here. Now there are three property functions: risk name, risk units, and risk static. The name and units will appear in at-risk graphs and reports. The static value is the value you will see when the at-risk dice button is toggled to static. 99. Another important property function that can be used with input distributions is the RiskCormat function. This allows you to induce correlations between various inputs. The easiest way to do this is through the Define Correlations button on the at-risk ribbon. Because this is such an important topic, it is discussed in more detail in the Correlated Inputs video in the guided tour series. You shouldn't feel obligated to memorize or even learn all of the available property functions in at-risk. Some are quite specialized, and you might never need to use them. However, you should at least be aware of property functions, and you should not be surprised when you see them tacked on to familiar input distribution functions and risk output functions. One area of particular interest to many analysts, particularly in a manufacturing setting, is quality control. The various methodologies that have been developed in the past few decades have been given many names and acronyms, but a particular favorite is Six Sigma. At-Risk incorporates a number of common quality calculations with its collection of Six Sigma functions. You can see a list of them in the Six Sigma group under the Insert Function dropdown on the At-Risk ribbon. All of these. This video will explain how to use these functions and what they mean. The example shown here is used to illustrate Six Sigma functions. This is for a process that makes parts. The parameters in cells C10 and C11 indicate how the process is producing normally distributed parts. Mean 100, standard deviation 0.5. A typical part diameter is generated in cell C18 with a risk normal function. The parameters in cells C3 to C7, especially the first three, indicate how the company would like to produce parts. They would like the parts to have an average diameter of 100, and they consider any part beyond the LSL and USL specification limits to be defective. The 0,1 values in cell C19 to C21 indicate whether a typical part is within specification limits, below the LSL, or above the USL. And these three cells have been designated as at-risk output cells. The process with these particular parameters is called a 3 sigma process because the mean of the process is 3 standard deviations from each specification limit. These values are indicated in cells C14 and C15. You would expect a 3 sigma process to produce very few defective parts because a normally distributed value has a very small chance of being more than 3 standard deviations from its mean. As the Six Sigma functions will indicate, however, a 3 sigma process is not necessarily as good as you might think. The key to using the at-risk Six Sigma functions is to append the risk Six Sigma property function with arguments in cells C3 to C7 to the risk output function when the part diameter in cell C18 is designated as an at-risk output. To do this, you select cell C18, click the Add Output button, click its FX button, and click the Six Sigma tab, and then you fill the dialog box out as follows. You refer to all of these cells, actually, the italics indicate that these values are cell references, as you just saw. And the value in cell C7 actually has no effect on any of the results shown in this video. Its role is quite limited. You then see that the risk output function in cell C18 includes the property function, risk Six Sigma, with those parameters. This addition of the property function has 2 consequences. First, when you run the simulation and then browse the part diameter cell, you will see the LSL, target, and USL superimposed on the graph. There they are. And I will move the sliders so that they are at the specification limits. As you can see, there are very few defectives. Keep in mind, however, that the given LSL, target, and USL are fixed. They are engineering specifications for this part. However, if the company's process mean is off target and/or its standard deviation is larger, the picture won't be nearly this nice. Here is an example where I will change the mean to 100.5 and the standard deviation to 0.75. Now I will rerun the simulation. Again, the sliders are positioned at the specification limits, and you can see that there are clearly a lot more defectives, most of them on the high end. Now I will set the mean and standard deviation back to their original values. And I will rerun the simulation again. Look at the summary statistics in column F. The first 5 are nothing new. They simply apply risk mean and risk STD, DEV, standard deviation, to the output cells. But from row 11 down, you see the second consequence of the risk Six Sigma property function. It enables you to use the Six Sigma functions. Their names are spelled out in column E. Each takes an argument, which is the part diameter cell. There are other Six Sigma functions besides these, but the ones shown here are the most common. Probably the two most common measures of quality are the CP and CPK indexes. The first of these, CP, is relevant for a process where the mean is on target, as it is here. It is scaled to be 1 for a 3 sigma process and 2 for a 6 sigma process. Larger values of CP are good and smaller values are bad. The CPK index is for a process where the mean is nearer to one spec limit than to the other. In this case, there is a CP type value for each limit, shown in cells C13 and C14. And CPK is the smaller of these. You will see an example shortly of such a process. The values in cells C16 to C18 are parts per million defective total, below the lower spec limit and above the upper spec limit. Similarly, the values in cells C19 to C21 are probabilities of defectives, either total, on the lower end, or on the higher end. Remember again that the numbers shown here are for a 3 sigma process, but even for this good a process, there are about 2,800 defective parts per million. This is why companies like Motorola decided that 3 sigma was not good enough. They strived for and achieved 6 sigma processes. But before seeing a 6 sigma process, change the mean to 100.5 so that it is closer to USL than to LSL and rerun the simulation. Now CP isn't relevant because the mean is off target. The relevant index is CPK, which is based on the distance from the mean to USL, the closest spec limit. And it is well below 1. Now the bad parts, and there are a lot of them, are on the high side. There is one famous number you might have heard in quality control settings: 3.4 defectives per million parts. This number arises from 2 conditions. First, the process is assumed to be a 6 sigma process. However, the second condition is that the mean might have shifted off target by as much as 1.5 standard deviations. The idea is that a shift of this magnitude might take a while to recognize. At-Risk lets you simulate such a shift with its long-term shift parameter in cell C6. So for this example, you enter the mean and standard deviation as 100 and 0.25 to get a 6 sigma process, and you enter 1.5 as the shift. When you run the simulation, you get the results shown here. Specifically, you get approximately 3.4 defectives per million in cell F16. Any company that can achieve this level of quality is truly first-rate. You might have used some of Excel's built-in functions for calculating probabilities or percentiles for theoretical distributions. For example, the normDist function finds left-hand tail probabilities for a normal distribution, and the norminv function looks up percentiles for a normal distribution. Here are a couple of examples. @RISK provides similar RISK-Theo functions, where Theo is short for theoretical. These functions are described in this video. Recall that when you open a distribution from @RISK's Define Distributions window, you see a graph such as the one you see here. It includes a variety of summary measures in the right pane. These summary measures are the values calculated by the RISK-Theo functions. You can find a list of all RISK-Theo functions in the theoretical group under the Insert Function dropdown on the @RISK ribbon. For backward compatibility with previous versions of @RISK, several of these are equivalent. Specifically, RISK-Theo P to X and RISK-Theo Q to X are equivalent to RISK-Theo percentile. Each finds the percentile of the distribution for a specified percentage. Also, RISK-Theo percentile D, D for descending, is essentially equivalent. If its percentage argument is, say, 0.05, it returns the 95th percentile. Similarly, RISK-Theo X to P and RISK-Theo X to Q are equivalent to RISK-Theo target. Each finds the probability to the left of a given value. RISK-Theo target D finds the probability to the right of a given value. The worksheet you see here illustrates several examples of RISK-Theo functions. Each of the cells in green font in row 2 contains an @RISK distribution function with the parameters shown below it. Then various RISK-Theo functions are used in rows 9 to 16 to calculate various summary measures of these distributions. RISK-Theo mean, standard deviation, minimum, maximum, 5th percentile, 95th percentile, which I've done with the D version using the 0.05 argument, the probability of being at least 2 standard deviations below the mean, Theo target, and the probability of being at least 2 standard deviations above the mean. Here I've used the D version for the right-hand tail. Several of these return value errors. This is because the minimum or maximum of some of these distributions is unbounded. There are 2 things to note about RISK-Theo functions. First, they are not based on simulations. Simulation, after all, is all about estimating distributions of outputs that are functions of input distributions, often very complicated functions. In contrast, RISK-Theo functions operate only on the gallery of @RISK input distributions. In fact, RISK-Theo functions are essentially hardwired to these input distributions, so they return exact values, not estimates from a simulation. Second, the only arguments RISK-Theo functions accept are @RISK distribution functions. Again, this is because of the way they are hardwired to these distributions. To convince yourself of this, enter the formula equal 2 times B2 in cell B3. Now try taking RISK Theo mean of this. It doesn't work. You get an error. Actually, if this did work, you would have a gold mine. You would be able to find means of functions of input distributions without any simulation. So you wouldn't need simulation at all. Again, Theo functions have essentially the same value as Excel statistical functions like normDist and norminv. They allow you to calculate summary measures of many commonly used theoretical distributions. The advantage of Theo functions over Excel functions are that they have more functionality and they apply to more distributions. For example, Excel 2010 has a Weibull.dist function for calculating probabilities of a Weibull distribution, but it doesn't have a function for calculating the mean, standard deviation, or percentiles of a Weibull distribution. Also, it doesn't have any functions at all for many of the lesser-known distributions in at-risk gallery, such as logistic, Pareto, PERT, and others. The risk SimTable function is often used to test several values of a decision variable so that a best value can be found. The at-risk RISKOptimizer tool can be used to take this a step further. It allows you to maximize or minimize a selected summary measure of any at-risk output cell by varying selected adjustable cells, where adjustable cells refer to values that can be varied to optimize the summary measure. For example, you can maximize mean profit, minimize the standard deviation of profit, maximize the 5th percentile of profit, or even maximize the probability of making profit greater than $500,000. This video introduces you to RiskOptimizer. It is a very powerful tool, and an entire chapter of a book, or even an entire book, could be devoted to it. To learn more, you can view the other RiskOptimizer videos in the guided tour series, and you can examine the many RiskOptimizer example files that accompany at-risk. First, if you are used to earlier versions of at-risk, you should realize that RiskOptimizer is now totally integrated into at-risk 6.0. You don't need to load it separately. It is in the Tools group of the at-risk ribbon. Note that the RiskOptimizer button is actually a drop-down. It provides the list of options you see here. To use RiskOptimizer, you must first set up an optimization model. This has been done for the airline revenue management model you see here, which is one of the at-risk example files. An airline sells discount and full fare tickets on a particular flight. The model assumes that all passengers will purchase discount tickets if they are available, but if they aren't, some passengers will be willing to divert to full fare tickets. The airline must choose limits on the number of discount and full fare tickets it will sell. It doesn't want to sell too many discount tickets because this will limit revenue from passengers who would be willing to divert to full fare tickets. Also, it doesn't want to sell too many full fare tickets because of potential overbooking. The model has been set up correctly, as you see here. There are uncertain quantities in the cells with green font. The total demand for tickets, the number willing to divert to full fare tickets, and the number of ticket holders who show up for the flight. The decision variables are in the cells with blue font. Any values can be entered initially. The single at-risk output cell is the profit cell. The goal is to use RiskOptimizer to find the values of the decision variables that maximize mean profit. To do this, you click the RiskOptimizer drop-down on the at-risk ribbon and select Model Definition. Then you fill out the dialog box as shown here. You must specify, first, whether to minimize or maximize. Second, an output cell, the profit cell. Third, a summary measure of that output to optimize. Mean has been chosen here, but as you can see, there are many other choices. Fourth, the adjustable cells and bounds on them. And fifth, any constraints. In this model, the goal is to maximize mean profit. The adjustable cells are the ticket limits in cells C19 and C20, and suitably wide bounds have been specified for them. Also, they are required to have integer values. Finally, there is a single constraint, used here mainly for illustration, that the fifth percentile of profit must be at least $10,000. In terms of adjustable cells, you actually have three choices under the values drop-downs: any, integer, or discrete. The any option allows a continuum of decimal values. The discrete option, with a step size of 5, say, would allow only the values 0, 5, 10, 15, and so on. This option can be used to speed up the optimization. To illustrate the mechanics, I will delete and then add an adjustable cell and the constraint. So I will delete this one, and I will add a new adjustable cell, C20. I'll put bounds, and I will require this to be integer. For the constraint, I will delete it and add it back. I'll describe it as percentile for profit. It's based on profit. The measure is the percentile, fifth percentile, and I want this to be at least $10,000. There is the constraint. When you click OK on the model definition dialog box, nothing happens, at least not yet. This model definition dialog box just stores the settings. To actually perform the optimization, you will select Start from the RiskOptimizer dropdown. First, however, you can select Settings from the RiskOptimizer dropdown. This opens the dialog box you see here. You can experiment with these settings, especially the runtime settings, but the default settings usually work fine. More details about the RiskOptimizer's settings are discussed in a companion video in the guided tour series. Now you can select Start from the RiskOptimizer dropdown to perform the optimization. RiskOptimizer can take some time to converge to an optimal solution. This is because it systematically checks many values of the adjustable cells, and for each it runs a simulation with the number of iterations you specify. As it runs, you see the progress in the blue text box and also in the progress dialog box. In particular, its bottom two boxes show the original mean profit and the best mean profit so far, so you can monitor these for progress. And if you click the magnifying glass, you can see progress in a more graphical form. Okay, it just quit. When the optimization stops, you see this dialog box with self-explanatory options. You would usually just click OK. For this airline model, the optimal solution is to limit the number of discount tickets to 109 and the number of full fare tickets to 53. The corresponding mean profit is $20,160. However, you shouldn't take these values too literally. First, they depend on the particular random numbers generated during the optimization. Another run might produce slightly different results, just as in any at-risk simulation. Second, the objective in many RiskOptimizer models, including this one, is fairly flat in the neighborhood of the optimal solution. Therefore, other solutions could have similar values of mean profit. If for any reason you would like to restore the original values of the adjustable cells, you can select Reset from the RiskOptimizer dropdown. If you look again at the model definition dialog box, you see that it shows Recipe above the adjustable cells. This is one of several solving methods available in RISKOptimizer, and it is by far the most common. The recipe method treats each variable as an ingredient in a recipe, and it tries to find the best mix by changing each variable's value independently. However, there are other solving methods, each designed for a particular type of optimization model, and examples of them, drawn from the at-risk example files, are discussed in a companion video in the Guided Tour series. This video illustrates some options for defining your RISKOptimizer model in the Model Definition dialog box. If you haven't already done so, you should view the RISKOptimizer introduction video in this Guided Tour series first. The airline revenue management model that was used in the earlier video is used again here for illustration. Specifically, the objective is to maximize mean profit, and there is a constraint that the 5th percentile of profit must be at least $10,000. Note that the mean profit and the 5th percentile of profit have been calculated in cells F22 and F23 with the risk mean and risk percentile statistical functions. Their values are currently meaningless, but they will become meaningful when a simulation is run. Actually, it is not necessary to calculate these summary measures in the worksheet itself, but it is done here to show the flexibility of the RISKOptimizer model definition options. One way to specify the objective, possibly the most natural way, is shown here. The specified cell is the profit cell, F20, and the specified summary measure is its mean. If this method is used, the risk mean function is not necessary in the model worksheet. Alternatively, a completely equivalent method is the following. Here you specify the risk mean cell, F22, and the value summary statistic. Of course, this does require you to use the risk mean function in your model worksheet. So those two methods are completely equivalent. Constraints are similar. This dialog box shows one way to specify the 5th percentile constraint. You select the profit cell, F20, and you specify its summary statistic to constrain, the 5th percentile. Alternatively, you can specify the cell as the 5th percentile cell, F23, and again use the value option. Again, they're completely equivalent. The main point is that RISKOptimizer provides a lot of flexibility for specifying the objective and constraints. This just might enable you to do something you didn't think you could do. As one possible example, suppose you specify the returns from two financial portfolios as output cells, and you want to maximize the difference between their standard deviations. Then you can calculate the standard deviation of each return with the risk std-dev function, calculate the difference between these two summary statistics, and specify this difference cell with the value summary statistic as the cell to minimize. There are even more options for constraints, including hard versus soft constraints, and simple versus formula in the entry style dropdown. The soft and formula options aren't commonly used, but you can read about them in the at-risk help files. This video discusses the various solving methods available in RISKOptimizer. If you haven't already done so, you should view the RISKOptimizer introduction video in this Guided Tour series first. The example it illustrates uses the common solving method, the recipe method. The recipe solving method treats each variable as an ingredient in a recipe, and it tries to find the best mix by changing each variable's value independently. However, there are several other solving methods, each designed for a particular type of optimization model, and examples of them, drawn from the at-risk example files, are illustrated here. This video won't actually show the optimization and final results. Its only purpose is to illustrate the types of solving methods available and how to set them up. You can perform the actual optimization in the RISKOptimizer example files. The order method. The order method is probably the second most popular solving method, behind the recipe method. It is used in models where the goal is to find the best permutation, or ordering, of a set of tasks. An example is shown here, where the goal is to find the best ordering of jobs with given due dates to minimize some aspect of lateness. To specify the model definition, you select the job indexes in row 11 as the adjustable cells, you click the Group button, you select Edit, and you specify Order as the solving method. There are the choices. That's all. And it looks like this, the order solving method for these indexes. Then it will find the best ordering, the best permutation of the numbers 1 through 10 to minimize some aspect of lateness. A RISKOptimizer model can actually have several groups of adjustable cells, each with its own solving method, but all of the examples illustrated in this video have a single group. Once you have a set of adjustable cells and you want to change its solving method, you select Edit from the Group command. If you want to identify a new set of adjustable cells with a different solving method, you would select New from the Group command. The project method. The project solving method is very similar to the order solving method, except that certain items or tasks must precede others. The project solving method can be used in project management to rearrange the order in which tasks are carried out, ensuring that the order will always meet the precedence constraints. It can also be used in other contexts, such as the example shown here. This model is a variation of the classical traveling salesperson model, where a salesperson must start in one town, end in another town, and visit each town exactly once. There are precedence constraints on the route, right here. For example, towns 23 and 7 must be visited before town 3. The objective is to minimize the mean total hours traveled. Uncertainty is introduced by letting the speed on any leg of the trip be normally distributed with mean 55 miles per hour and standard deviation 5 miles per hour. As in the order solving method, the goal is to find a permutation of the town IDs, those in column G. However, only permutations that satisfy the precedence constraints are allowed. For example, in the solution shown, town 35 is visited first, town 29 is visited second, and so on. So, because of the precedence constraints, town 3 must be further down the list than either town 23 or 7. This is exactly what the project solving method ensures. You can see that this solution isn't allowed because, for example, town 7 is visited before town 13. And the precedent says it should be the other way around. You choose the adjustable cells and solving method exactly as in the previous order example, but now you must indicate the preceding tasks range when you specify the adjustable cell settings. So it's using the project solving method, but the tasks range is columns I to K, right here, the precedence constraints. And again, RISKOptimizer will find a permutation of these indexes that satisfy the precedence relationships and minimizes mean total hours traveled. The budget solving method. The budget solving method is useful when the adjustable cells, or some subset of them, must sum to a fixed number, such as 100%. In such cases, the recipe solving method could be used with a constraint on the sum, but the budget method eliminates the need for this constraint. It finds first the sum for the original values of the adjustable cells, and it maintains this sum throughout the optimization. The model shown here is a financial retirement planning model. The details can be found in the Planning for Retirement example file. But the important aspect for now is that the adjustable cells, the weights for the person's portfolio in row 8, must sum to 100%, as they do in this initial solution. Therefore, these adjustable cells are specified to be between 0 and 1, and the budget solving method ensures that they will always sum to 1, that is 100%. The grouping method. The grouping method is a specialized solving method for cases where you want to find an optimal grouping of items. In the model shown here, the goal is to assign each of 80 securities to one of 5 groups so that the groups are as even as possible. Specifically, the total future value of each group is calculated in column J, and the objective is to minimize the standard deviation of these totals. This is a perfect candidate for the grouping solving method. The model definition is shown here. Each adjustable cell in column G indicates which group the security has been assigned to. The grouping method is used. Note that RiskOptimizer determines the possible groups, in this case 1 to 5, from the distinct values in the adjustable cell range. Alternatively, you can specify the range of group IDs as shown here. The schedule method. The schedule method is another very specialized but also very powerful solving method. It can be used to find the optimal scheduling of events when there are constraints on which events must occur with other events, that is at the same time, before other events, and so on. The model shown here is an example, and you can learn more about it in the Scheduling Classes with Uncertainty example file. Each adjustable cell in column F indicates which time slot to assign to each class, and the objective is to minimize a penalty function, a combination of the number of excess classes that can't fit in available rooms and excess students that can't be accommodated in the classrooms. The constraints are spelled out in the constraint table. The 3 chemistry classes must be scheduled at time slot 1. The 3 biology classes cannot be at the same time slots as the 3 corresponding chemistry classes, and the 3 history classes must be at the same time slots as the corresponding sociology classes. The model definition is shown here. The time slots in column F are the adjustable cells. The scheduling method is used. There are 6 time blocks allowed, and the constraint cells come from the constraint table. So again, this method is very specialized, but for models like this one, it can be very useful. Again, you will probably use the default recipe solving method for the majority of your RiskOptimizer models. But the solving methods discussed here provide a tremendous amount of flexibility on the types of models you can optimize. This video briefly discusses the optimization settings that you can choose for your RiskOptimizer models. If you haven't already done so, you should view the RiskOptimizer introduction video in this guided tour series first. You can view or change settings from the RiskOptimizer dropdown. This opens a dialog box with 3 tabs. The Runtime tab provides settings on when to stop the search for the optimal solution. In general, it is difficult to know how long to run a RiskOptimizer optimization. It often finds a very good solution fairly quickly and then spends a lot of time trying to find slightly better solutions. You can experiment with the runtime options, but the one shown here, the default of running 1,000 trials and then stopping, often works fine. Of course, if you notice from the progress window that the objective is still improving as the optimization stops, you can increase the number of trials. The Engine tab, shown here, allows you to choose between two optimization algorithms, a genetic algorithm or the OptQuest algorithm. Here you see them. The OptQuest algorithm is new to At-Risk 6.0, and it is often superior to the genetic algorithm in terms of speed. If you select Automatic, the default option, RiskOptimizer will choose the algorithm that it thinks is best for your particular model. You can override this automatic choice, as shown, but you should understand the options well before doing so. You can read more about these algorithms in the At-Risk help files. Finally, the Macros tab allows you to run macros during the optimization process. However, you have to write the macros in Excel's VBA programming language, so this option is for advanced users. One final option you see in the RiskOptimizer dropdown is Constraint Solver. This is useful when the genetic algorithm is being used and there are constraints in the model. If the original solution is not valid, that is, the values in the adjustable cells do not satisfy the constraints, the algorithm might have to run many simulations just to find a valid solution. In this case, Constraint Solver can be run first. It runs an optimization in a special mode, where the goal is simply to find a valid solution, and it quits as soon as a valid solution is found. Then, starting from this valid solution, the regular RiskOptimizer algorithms can be used to find the best solution. Probably the most significant addition to At-Risk 6.0 is its new set of time series tools. These allow you to fit time series processes to time series data, and they enable you to define time series processes as inputs for a simulation. These new tools are analogous to the existing distribution fitting and define distributions tools. Just as the distribution fitting tool lets you fit a distribution to a column of data, the time series fit and batch fit tools let you fit one or more time series processes to one or more columns of time series data. Similarly, just as the define distributions tool lets you choose a distribution for an uncertain input, the time series define tool lets you choose a time series process for a set of time series forecasts. Fit. The time series fit tool is used to fit a time series process to a single time series variable. The example illustrated here is of the monthly Dow Jones Industrial Average since 1990. Note that the time series data often has a date column at the left. Although it is not absolutely necessary, it is useful to separate this date column from the time series column or columns with a blank column. You certainly don't want to fit the date column, and this blank column decreases the chances that you inadvertently include the date column in the data range to be fitted. To fit the Dow data, select any cell in column D and select Fit from the time series dropdown on the At-Risk ribbon. This leads to the dialog box you see here. It shows a graph of the series and graphs of two important related quantities, the autocorrelation function, or ACF, and the partial autocorrelation function, PACF. These are useful for identifying the type of time series you have. The theory behind fitting assumes that your time series is stationary. This means that its mean and variance are constant through time. It also means that there shouldn't be any seasonality. Often these assumptions are violated. For example, you can see that except for two downturns, the Dow has been trending upward. It is definitely not stationary. Therefore, the original Dow series cannot be fit directly. It must first be transformed to make it stationary. The middle left section of the dialog box helps you do this. You can check any of the options, such as detrend, to induce stationarity, or you can click the Auto Detect button to have at-risk do it for you. When you click the Auto Detect button, the dialog box changes, as you see here. Now a logarithmic transformation is performed to stabilize the variance, and first-order differences are taken to get rid of the trend. As you can see, the resulting series in red is essentially noise now. And the ACF and PACF graphs have also changed considerably. The transform series is now ready for fitting. At this point, you can click the Fit button directly, or you can click the Series to Fit tab. It shows all of the candidate processes in at-risk's time series collection. These include autoregressive and moving average processes, Brownian motion and variations of it, and autoregressive conditional heteroscedasticity processes. As in the gallery of distributions you see in the Define Distributions window, you can check or uncheck as many of these as you like. At-risk will try fitting each of the checked ones to the given time series. Now I will click Fit. Here are the results. For each of the checked processes that make sense for this particular time series, at-risk finds the best fitting member, such as the best MA1 process, and it ranks these according to a fitting criterion. In this example, it uses the AIC criterion. For the Dow series, the moving average process of order 1, MA1, using the parameters above the graph, right here, provides the best fit. You can see its projection into the future in the right section of the graph. The legend helps explain this. The 4 buttons at the bottom left provide more options. The left 2 are the usual Help button and the Edit and Export button. The 3rd button is for synchronizing. Instead of having the forecasts start after the last historical observation, you can have them start at the beginning of the historical data, as shown here. You are essentially forecasting known values as well as future values. Finally, the 4th button is for animation. When it is toggled on, you see a series of red random sample paths in the graph. If you want to generate future forecasts in your worksheet, you can click the Write to Cells button and then specify a range. For example, the forecasts here are for the next 12 months. These forecasts are live. At-risk enters an array formula in the specified range that contains the risk MA1 function with the parameters you just saw. You can see it is an array function because it has the curly brackets around it. And that array function is in this whole range. Because this is entered as an array formula, it works as a unit. For example, you can't delete the contents of a single cell in the range. You would have to delete them all. As usual with at-risk distributions, static values appear in the range unless you toggle the at-risk dice button to random. Then they jump around. These future forecasts can now be used as inputs to an at-risk simulation, just like any other input distributions are used. Batch fit. The time series dropdown also has a batch fit item. This enables you to fit multiple related time series all at once. This not only saves time, but it has the extra benefit that it estimates correlations between the time series. The data shown here of monthly bond yields of AAA and BAA bonds can be used to illustrate the batch fit tool. To fit both series at once, select any cell in column D or E and select Batch Fit from the Time Series dropdown. This brings up the dialog box you see here. Again, the date column has been separated from the time series data by a blank column, so at-risk guesses correctly that the data range is in columns D and E. It doesn't include the date. The issue of stationarity still applies, but now it is trickier because multiple time series are involved. One transformation might be required for one time series, and another transformation might be required for another. If you manually check the transformation options, such as the logarithm transformation, your choices will be applied to each of the time series. Therefore, it is usually better to check the auto-detect option. At-risk will then try to find the best transformation, if any, for each time series separately. If you use this option, you don't see the transformations selected in this dialog box, but they are shown in later results. For this dataset, you see this message when you check the auto-detect option. As it indicates, no set of transformations can be found to make the variant stationary. This sometimes happens, usually because of large swings in some part of the series. In this case, you can click OK and hope that the fit will still be adequate. The Series to Fit tab is the same as before, but now there is a Report tab. It provides several options, including the important option of estimating correlations between the time series. I will place the results in the active workbook. Once you click the Fit button, the main results are placed on a time series fit summary sheet shown here. The top part shows the best fitting processes, MA1 and again MA1. And starting in the function row, there are again live array formulas for future forecasts. Again, the curly brackets for array functions. As before, these can be used as inputs to a simulation. The bottom section shows the correlation matrix, which is an argument in the array formulas. There's RiskCormat. If you check the first option in the Report tab, you also get a separate worksheet for each time series, showing the details of the fits for each candidate process. Define and results. If you use the time series tools to generate forecasts for use as inputs in a simulation, you will probably do it as explained so far. That is, you will probably fit processes to historical data and then use future forecasts from the best fitting process as simulation inputs. However, if you have a sufficient understanding of the various processes, you can choose one directly for a simulation by using the time series define tool. Again, remember how the define distributions tool works. You choose a distribution, such as the triangular distribution, along with values of its parameters, for use as an input cell. In the same way, you use the time series define tool to choose a time series process, along with values of its parameters, for use as a time series input range. To use this tool, select Define from the time series dropdown. This brings up the dialog box you see here. Then you choose one of the processes, such as AR1, and click the Select Series button to bring up the next dialog box. Here you can supply a name, a range where you want the forecasts to be placed, and the parameters of the AR1 process. It is not as straightforward to choose these parameters as, say, the parameters of a normal distribution. You have to have some understanding of the various time series processes. The at-risk help provides some explanations of these processes, but you should still have some background in time series theory before you use this define tool. The forecasts are then generated in the requested range, such as you see here. They then become inputs to a typical at-risk simulation. In this case, the goal is to find the distribution of the total procurement cost over the next 24 months. Again, a live array formula is entered for the prices, and usual, that is non-time series, at-risk distributions can be entered elsewhere, such as for the units produced. I'll now run the simulation. Besides the usual at-risk results, you can click Results from the time series dropdown to get a report like this one. This is in addition to any of the other usual at-risk reports for simulation results. You can experiment with the buttons at the bottom of the window to show information about the time series data generated during the simulation. For example, now I am seeing overlays of the time series prices that were generated during the different iterations. The project tool in at-risk allows you to analyze your project schedules for risk. This is done by linking the simulation capabilities of at-risk with the scheduling capabilities of Microsoft Project. Using the project tool, you can answer questions such as, what is my expected project completion date? Or, what is the probability of finishing more than 3 months late? You can also determine the critical factors that affect the risk of a project so that you can plan mitigation strategies. Note that Microsoft Project, any version from 2003 through 2010, must be installed on your PC before you can use at-risk's project tool. In fact, the project dropdown won't even appear on your at-risk ribbon unless Microsoft Project is installed. It is installed here. Also, to use Microsoft Project together with at-risk, you cannot be running the 64-bit version of Excel 2010. Only the 32-bit version is supported at this time. When you use at-risk's project tool, you first need a schedule created in Microsoft Project. Typically, you already have a project that was developed without including uncertainty. In other words, you will probably have a deterministic project, where all elements in the schedule have fixed values and a single completion date is generated. These schedules are saved in MPP files. At-risk's project tool imports your schedule's MPP file from Microsoft Project into Excel. Once in Excel, at-risk distributions can be added to the schedule so that a risk analysis can be performed. By using at-risk functions and Excel formulas, you are able to create better, more robust risk models than can be built in Microsoft Project alone. In addition, you can access all of the capabilities of at-risk when you work with project schedules. The schedule shown here is in Microsoft Project. It is stored in the file tutorial.mpp, available from the at-risk example files. To import this project into at-risk, you select Import MPP File from the Project dropdown on the at-risk ribbon and locate the file. Note that this file doesn't need to be open in Microsoft Project. In fact, Microsoft Project doesn't even need to be open, but it will launch and open this MPP file when you do the import. You can click No when you are asked if you want to review import settings, and you can click Yes when you are asked if you want to save the import as an Excel file. I won't do so. Note that this Excel file retains a link to the MPP file. When you open this Excel file again with at-risk loaded, Microsoft Project will automatically launch and open the MPP file. What you see here in Excel is similar to what you saw in Microsoft Project. The tasks in the schedule with their durations and their start and finish dates, and you even see the Gantt chart that has a bar for each task. A second Excel worksheet lists the resources used by the project. As mentioned earlier, the imported project is also open in Microsoft Project. This is because At-Risk uses Microsoft Project to perform scheduling calculations when it runs its simulations. When using At-Risk, your original schedule stays in Microsoft Project, and the model for the risk analysis is built in Excel. Formulas and functions can be added to cells in Excel where the task and resource dates and values are shown. You can now add probability distributions to the durations of selected tasks. For this example, I will add discrete distributions to 3 of the task durations. The distributions used can be any reasonable distributions, but for this illustration, I want them to have enough variation so that you can see some range in the simulation results. So I will add discrete distributions to these 3 cells. I'll make them all risk discrete with possible values 4, 5, 6, 7, and relative probabilities 1, 4, 3, 2. Copy that to each of those 3 cells. The most likely value is still 5, but now there is variation around this. Then, just as in any at-risk model, you can specify 1 or more output cells. For a project, this will often be the finish date of the project. Your objective is to determine the range of possible dates for project completion, and possibly the likelihood of completing by a specified date. For this illustration, I will add the finish date in cell E2 as the single at-risk output cell. Now you can simulate your project by clicking the Start Simulation button. During a simulation, At-Risk for Excel communicates with Microsoft Project, sending Excel values sampled from distributions and calculated in formulas to Microsoft Project. In Project, these values are inserted into the schedule and the schedule is recalculated. New output values calculated by Project are sent back to Excel so that they can be collected as simulation results. Now you can explore the results of the simulation. For example, you can see that there is about a 4.5% chance that the project won't be complete until after November 13th, because this is the beginning of November 14th. Also, a tornado chart shows that the variation in the top 2 tasks is much more responsible for variation in the project completion date than variation in the bottom task. When you work with the project tool, you have access to all the usual reports available in At-Risk. For example, you can generate quick reports of simulation results. You can create charts in Excel and reports on simulation data and sensitivity analyses. In addition, there are some new reports that are specific to project simulations. One of these is the probabilistic Gantt chart. A probabilistic Gantt chart shows, by default, the earliest, 10th percentile, and expected start date, and expected 90th percentile and latest finish dates for project tasks. It is shown in a format similar to the Gantt chart you see in both Microsoft Project and Excel. To display this chart for a simulated project, you select Probabilistic Gantt from the Charts and Reports group in the project drop-down list. This brings up the dialog box you see here with various options, and you can click OK to see the following modified worksheet. The probabilistic Gantt chart shows both the original deterministic schedule in blue and the simulated range in red. The small solid red bar for each task shows the range between the earliest possible start date and the latest possible finish date. The lightly shaded red bar for each task shows the range between the start date 10th percentile and finish date 90th percentile. The two red diamond markers for each task show the mid start and finish dates. In this case, the mid values are the means, but you can redefine them in the probabilistic Gantt chart settings dialog box. The critical index column shows the percentage of time that each task is on the critical path. Any delay in a task on the critical path will delay the project as a whole. In a deterministic schedule in Microsoft Project, a task is either critical or it isn't. However, when a project is simulated, the critical path can change in each iteration as values in the schedule are changed by at-risk. The critical index ranges from 0% to 100%. Tasks with a high critical index are more likely to cause delay to the project because they are more likely to be on the critical path. It turns out that all of these are 0 or 100%, but it can easily happen that percentages are between 0 and 100%. This video has just begun to illustrate the many options in the at-risk project tool. You can see more of its features in the project examples in the at-risk example files. At-risk's project tool includes several modeling tools that make it easy to apply ranges of possible values to schedule estimates. One of these, the parameter entry table, is the topic of this video. It creates a table where you can enter ranges of possible values for items such as task durations. To use a parameter entry table, you first need to import a project into Excel. To do this, you should select Import MPP File from the Project dropdown on the At-Risk ribbon and locate the file Parameter Entry Table MPP available from the At-Risk example files to import this project into Excel. I won't save this file for right now. Then you should select Parameter Entry Table from Model Tools on the Project dropdown of the At-Risk ribbon. The goal is to create columns next to your schedule where you can enter values such as minimum, most likely, and maximum values for task durations or other schedule values. As you can see, there are a variety of options you can use when creating a parameter entry table. The Field dropdown lets you select the type of data you want to enter ranges of possible values for. For now, you can select task duration, a common source of uncertainty when scheduling. The Using Distribution section lets you select the at-risk distribution that will use values from the table. These values will create a probability distribution that specifies the range of possible values for each task's duration and their relative likelihood of occurrence. You have many options here, but for now you can use the triangular distribution, which takes minimum, most likely, and maximum possible values as arguments. You can also select a variation that will be shown in the values in the table when it is created by at-risk. By using 10% below and 10% above, you are specifying that the minimum and maximum of each triangular distribution are respectively 10% below and 10% above the most likely value, which is the original deterministic value in the schedule. In any case, you are not limited to this default range. Once the table is created, you can edit the table values directly in Excel to customize the range for any task. In the Build Entry Table section, you can choose to build a parameter entry table for all tasks in your project or just selected ones. For some projects, you might want to apply a range of possible values to every task in the schedule. For others, you might want a table only for a group of tasks. For this illustration, the parameter entry table will be built for all tasks. When you click OK, you get a warning about overwriting values with distributions. You can click OK for this. Then your worksheet in Excel includes 3 extra columns where the minimum, most likely, and maximum values for task duration are shown. Also, risk trying distributions have replaced values in all task duration cells. At this point, you can change the values in the parameters entry table as you like. Because they are arguments to the risk trying functions, these distributions will change automatically. Now I will add an at-risk output and run the simulation in the usual way. It is easy to update your parameter entry table to see how simulation results change under different assumptions. For example, you might want to apply a 50% maximum rather than the previous 10% maximum to each task duration to see how results change when there is a higher probability the tasks will take longer than expected. All I have to do is change this to 50%. Overwrite? Yes. Now the maximums are higher. Another useful option is to add the table to your MPP file. This option is at the bottom of the parameter entry table dialog box. Again, I'm warned about overwriting. That's okay. I won't save the table. Now if I look at project, I see that it has 3 new columns for the parameter entry. From here, schedulers can enter their estimates without having access to your Excel model. So a scheduler might change this value to 150. Later, when you reopen your Excel workbook, the MPP file will automatically be opened and its new estimates will be updated to your Excel spreadsheet. Alternatively, you can select Sync Now from the project dropdown on the at-risk ribbon to update your Excel spreadsheet with new values from the MPP file. There's the new value. So now they are in sync. At-Risk's project tool allows you to build a risk register that can be included in a simulation of a project schedule. A risk register lists possible risk events that can impact a project schedule and its costs. Typically, each risk event has a probability of occurrence, so that it either occurs or it doesn't. If the risk occurs, the size of the impact of the risk is typically also uncertain. To learn about risk registers, you can open the Excel file Simple Risk Register. This file is in the at-risk example files and is linked to a project MPP file of the same name. It has already been opened here. Remember that this also opens the corresponding MPP file in Microsoft Project. An Excel worksheet is a good place to build a risk register. The row and column format makes entering a table of risks straightforward. At-risk can be used for defining distributions that determine whether a risk occurs, and if so, the size of its impact. In this case, the probability column shows the probability of a given risk occurring. Risk discrete distributions entered in the simulated occurrence column use this probability to sample whether a risk occurs. If a risk does occur, it causes a schedule impact, sampled from a risk PERT distribution with min, most likely, and max values shown in the schedule impact columns. The risk can also have a cost impact, sampled from a risk trying distribution with min, most likely, and max values shown in the cost impact columns. Of course, you can use any of at-risk's distribution functions to model impacts in a risk register. Once you have built a risk register, you need to link it to your project schedule. There are different ways to create the link. The simplest method is to add a simulated schedule or cost impact directly in a formula in Excel. This method is used for the environmental risk in row 6. The corresponding link is in cell C5 of the tasks sheet. During a simulation, this formula calculates the duration of the cleanup task by summing two values. First, the PERT distribution generates a base distribution from 25 to 35 days. Then the impact of the environmental risk from the register is added, but only if this risk occurs. Risks from a register can also be linked to a schedule using RiskProject functions. One of these functions is called RiskProject add delay. The effect of this function is to add an additional task and associated costs to the schedule if a risk occurs. The idea is that a risk event often does not directly impact the schedule and cost of an existing task. The risk event can instead cause a new activity to take place, with its own duration and costs. In this example, the customer design approval risk in row 5 results in an additional task and associated costs being added to the schedule if the risk occurs. This new task will take place after the original design task, perhaps due to added design revisions and reviews. The new task has a varying length and cost as calculated in the register. When appropriate during the simulation, the at-risk function RiskProject add delay adds this new risk-related task after the design task. You can look at the formula in cell V5 on the register sheet to see this function. Its first argument is a reference to the task in the schedule where the new task will be inserted if the risk occurs. In this case, if the risk occurs, the new task will follow the design task, B3 in the tasks sheet. And the existing successor tasks to design will now come after the new task. It is as if a new task with its own duration and costs is dropped in the middle of the schedule when the risk occurs. A second RiskProject function called RiskProject add cost adds an additional risk-related cost at a time specified. When a risk event occurs, this function adds a cost only to the project's cost calculations. In this example, the material price risk in row 7 results in an additional cost being added to the project when this risk occurs. This risk could be additional raw material costs that are incurred anywhere within a specified time frame. When appropriate during the simulation, the at-risk function RiskProject add cost adds this new risk-related cost to the cost calculation in project. You can look at the formula in cell V7 on the register sheet to see how this function works. Its first argument is the amount of cost to be added. In this case, it is a reference to cell S7, which in turn has a formula that multiplies cells D7 and R7. Cell D7 determines whether the risk occurs, with a value of 0 or 1, and cell R7 determines the amount of the cost impact, sampled from a risk triangle distribution with min, most likely, and max values in the cost impact columns. Therefore, the amount of the cost impact is either 0 if the risk does not occur, or the value sampled from the risk triangle distribution. Note that a risk make input function is also used in cell S7. This helps with sensitivity analysis. At-risk uses cell S7 as a single input in its sensitivity analysis and tornado graph, instead of picking up the simulated occurrence and cost impact functions as separate inputs. You will see one bar in the tornado graph for the impacts of material price risk, even though this risk is defined by combining two separate distributions for simulated occurrence and cost impact. The linking of a risk register to a schedule is best shown during a simulation. First, you can toggle the at-risk dice button to random and then press the F9 recalculation key a few times as you watch the register. You will notice that the occurs cells turn red when a risk occurs. The red is actually caused by conditional formatting. When a risk occurs, values are then shown in the register for the schedule and cost impacts. These are sampled from the at-risk distributions that have been added to the formulas in the register. Now I will run a simulation, and as it runs, I will open the Microsoft Project window. Two new entries have been added, one for customer design approval risk and one for material price risk. If you watch carefully, you will see that when the customer design approval risk occurs, a new taskbar appears in the schedule with the design task as its predecessor. The length of this new task changes depending on the size of the schedule impact of the risk. The bar enters and leaves the schedule depending on whether the risk occurs or doesn't occur. Similarly, when the material price risk occurs, a black diamond is displayed at the date the cost is introduced to the project. This cost is then added to the project's cost calculations. If you were tracking time-scaled costs during the simulation, you would see the new cost from the risk show up in at-risk's time-scale data report in the time period the risk occurs. As simulation becomes increasingly important in corporate settings, it is valuable to save inputs to simulations and results from simulations for later use or exploration. At-Risk allows you to do this with its library tools. An at-risk library is a SQL Server database, and it can hold corporate input distributions and simulation results. Of course, this requires a SQL Server account. If you don't already have an account, you can download a free version of SQL Server Express when you install At-Risk. The simple simulation model you see here, adapted from one of the at-risk example files, can be used to illustrate the at-risk library tools. It contains 3 input distributions and a single output. 3 inputs and 1 output. You can imagine that these input distributions are the result of much research and many expert opinions, and they might be reusable at later times in similar simulation models. Therefore, it makes sense to store them in a database. This is exactly what the library allows you to do. To add an input distribution to the library, you select one of the input cells and click the Define Distributions button on the At-Risk ribbon to get the usual window shown here. You can edit the information in this window, such as the name, as you like. Eventually, you should click this Book button, the Add Input to Library button. At-Risk shows this prompt, so you should click OK. Then it opens the At-Risk Library window shown here, displaying the input that is about to be added. As you can see, there is also a Revisions tab, so that you can store information about revisions to distributions as well. Again, you should click OK. There is the addition to the library. You can add as many input distributions as you want in this way. I will add 2 more. Then when you select Show At-Risk Library from the Library dropdown, you will see the following list of all distributions in the library. There they are. At this point, the Add button allows you to add a new distribution to the library, and the Edit and Delete buttons allow you to edit or delete existing distributions in the library. Also, you can click this button to enter one of the library distributions in a selected cell. Alternatively, you can add a library distribution to a cell through the Library tab of the Define Distributions window. Any of these. The At-Risk Library also lets you store results of simulations. To do this, you run a simulation and then select Add Results to Library from the Library dropdown. you get this dialog box. You can click the Properties button to see properties of the library. Then you click the OK button to save the results in the library. Finally, at a later time, you or your colleagues can see the saved results by selecting Show At-Risk Library from the Library dropdown. Select the Results tab. Select one of the results and display it in some way. You and your colleagues don't even need access to the original simulation file to see this. All that you need is access to the library, that is, the SQL Server database. This video discusses the options in the At-Risk Utilities dropdown on the At-Risk ribbon. As in all add-ins in the Decision Tools suite, the Utilities dropdown list includes items for unloading the add-in or loading other Decision Tools add-ins. It also allows you to change application settings. Each of these settings is for the at-risk application as a whole, not for the particular simulation model you are working on. These settings remain in effect on your PC indefinitely until you decide to change them again. As you can see from the Application Settings dialog box, there are many categories of settings, and you can expand or collapse any category by clicking its plus or minus sign. One particular setting you might want to change is in the Reports group. By default, At-Risk places report worksheets in a new workbook. If you would rather have it place them in the same workbook as your model, you can select the Active Workbook option. Again, if you do so, this setting will remain in effect until you change it back. Most of the default settings are perfectly adequate, and chances are you won't need to change them. However, At-Risk gives you plenty of possibilities, so don't be afraid to experiment. If you do experiment and you then want to restore the original default settings, this is easy. You just click the Save icon on the bottom left and select Reset. The Windows item displays a list of all open at-risk windows. I will create a few windows in this model to show how it works. There is the list of windows that are open. To see any one of them, I can activate it. I can rearrange the windows, or I can close them all. The Open Simulation File item lets you open a RSK5 file from an earlier version of At-Risk. This type of file was used to store simulation results, especially when the simulation was large and you didn't want to embed the results in your model file. The Clear At-Risk Data item opens the following dialog box where you can clear various items from your model workbook. Here it helps to realize that if you open an Excel file while At-Risk is open, even a file that has nothing to do with At-Risk simulation, and you then save the file, certain at-risk settings will be embedded in the file. When you open this file again, you might be puzzled if you are asked about at-risk settings, thinking that this file has nothing to do with at-risk. In this case, you can use the Clear At-Risk Data command and probably just check the Settings option and then save the file again. Then it will have no embedded at-risk settings. For the current model, I have run a simulation, so I will clear the simulation results. The swap-out functions item is a very handy utility that allows you to share at-risk models with colleagues who don't own at-risk. If an at-risk model is open that contains various at-risk functions, such as risk normal, risk output, and others, and you then use the swap-out functions command, you will see the following dialog box. If you click OK, a formula such as equals risk normal of 2000, 200 will become equals 2000. That is, the distribution will be replaced by its static value, usually the mean. All other at-risk functions, such as risk output, will disappear as well. Now that's static. There is no risk output function. Also, most of the buttons in the at-risk ribbon have been disabled, but there is a new swap in functions button on the left side of the ribbon. You can click it to restore the at-risk functions. If you save the file with the at-risk functions swapped out, the functions will be remembered, but your colleagues without at-risk won't see them. They will see only the static values. However, if you open the file again with at-risk loaded, you will be asked whether you want to swap the functions back in so that you can restore the model to its original form. Finally, the Convert Workbook item lets you convert spreadsheet models created with Oracle's Crystal Ball version 7.3 or higher into at-risk format. To use this feature, however, you must have Crystal Ball and at-risk installed on the same machine. Also, this feature is not compatible with 64-bit versions of Excel, at least not yet. You typically won't need to use this item. The reason is that when you open a Crystal Ball workbook when at-risk is running, and at-risk detects that Crystal Ball is installed, you will automatically be asked if you want to convert your model.